So on page 16, we've got a problem described for us here at the top. And we want to figure out for this particular scenario, a few sort of what we're going to call terms in our sequence. We're going to determine whether the sequence we've got is arithmetic or geometric. We're going to write a recursive and an explicit formula for our sequence. And then we're going to calculate a few future terms for the sequence. So here's our context. Here's our scenario. A party will have hexagonal tables placed together with a space for one person on each open side. So if I've got just one table, that would look something like this. And I could have a person sit on each side of this table. So if I have one table, I could fit 6 people, one person on each side. Does that make sense? Okay. If I add tables, I'm going to add them so that I have sides that meet together. So if I add a table, I would add it here. The person that was sitting here, I could just bump them out to the end on this side now. And then I could have more people sit at the additional open sides that I've got. So we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For 2 tables, we could have 10 people. If we had 3 tables, that configuration would look like this. And I could seat 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 people. Is anyone seeing a pattern emerge here? Yeah, every time I add on a table, whoever was at the end can just move out to the new end. And then I add 1, 2, 3, 4 additional seats. So every time I'm adding 4 new seats, every time I add a table, I add 4 new seats. So this would be 18 people I could seat with 4 tables. How many people could I seat with 5 tables? 22, good. So what type of sequence would this be? Why arithmetic? That's okay. Because we're adding the same amount each time. The sequence is arithmetic because we add arithmetic. We add 4 new seats with each new table. I add the same amount of seats every time I add a table. That makes this an arithmetic sequence. So now let's write some formulas that would represent this sequence. We're going to start with recursive. Remember, recursive is the one that's based on the previous term. So our recursive formula for this sequence, since we're adding 4 each time, would be a sub n equals a sub n minus 1 plus 4. So my new term would be the previous term, the one right before it, plus 4. And that's what we did to find our number of people for 4 and 5 tables. We took the previous one and we added 4. And to find 5, we took the previous one and added 4. That's our recursive formula there. For our explicit formula, remember, this is the one that's not based on the previous term, right? And for our arithmetic sequences, this is the one that kind of follows that same format as point and slope form. I'm going to write this based on our first term here. So our first term is 6, and then we're adding 4 each time. So for my recursive formula, this would be a sub n equals 4 times n minus 1 plus 6. I'm going to talk for just a second about why this kind of looks like point slope. So what we're doing here is adding 4 a bunch of times, right? I know I start with 6 people at a table. Every time I add a table, I add 4 seats. So if I wanted to figure out how many people could fit at 20 tables, I would have to add 4 a bunch of times, right? Start with 6 and then I add 4, add 4, add 4, add 4, add 4. What's another way that I could represent, even for just this portion? I want to add 4 3 times. What's another way I could write that? I want to add 4 3 times. Yeah, 4 times 3. We represent repeated addition with multiplication. So what we're saying here with our formula, and this is why it looks like multiplication, is we're saying we're starting with 6 people at a table. And then we're going to add 4 times however many tables we add. So if we add another table for our second term, right, we would plug 2 in here for that second table. 2 minus 1 would be 1. So we're going to add 4 1 time. If I want to add 20 tables, right, or I want to figure out how many people I can seat at 20 tables, that means we've got our original table of 6, and then we're going to take 4 times 20 minus 1 would be 19, since we're adding 19 new tables. Right? Multiplication allows us to represent that repeated addition. So now let's use our formulas to find a couple of future terms. A6 is actually the next term in our table. So if we wanted to, we could use our recursive formula and add 4, and we would get 26. I could also use my explicit formula here and plug 6 in for n. Remember when you're simplifying these to follow order of operations. So I need to work inside those parentheses first. 6 minus 1 would be 5. 4 times 5 is 20. Plus 6 would give us 26. And then same idea for a sub 30. How many people could I fit at 30 tables? I'm going to use my explicit formula here. That would be 4 times 30 minus 1 plus 6. Remember to follow your order of operations. Questions for me on page 16? Okay, let's take a look at another one. On the next page, page 17, same idea, just another scenario that we're going to look at. So on page 17, it says the piece of paper has an area of 80 square inches. A person cuts off 1/4 of the piece of paper. Then a second person cuts off 1/4 of the remaining paper. A third person cuts off 1/4 of what's left, and so on and so on. So I have my sheet of paper, and somebody comes up and tears off a fourth. Now I have whatever's left of my sheet of paper, and somebody comes up and tears off a fourth of what's left. And that keeps happening. People keep coming up and cutting off a quarter of my piece of paper. So I want to know, what's the area remaining for my piece of paper after all these people have cut pieces off of it? So before anybody takes anything off of my paper, I've got 80 square inches in area, right? We're starting, before any cuts have been made, we're starting with 80 square inches. Now, that first person that takes a quarter of it off, I want to know what's left, okay? So what's left after that first person? What are we thinking here? What are you trying? Nate, what'd you try? Eighty times 1/4. So 80 times 1/4. 1/4 is the part that they tore off. So then what did you get when you did? So you found what's a fourth of 80? That's the part that they took away. A fourth of 80 would be 20. And then you said, well, they took away 20. So 80 minus 20 leaves us with 60. Perfect. How about after that second person rips a chunk off of my paper? What do I have left after the second person? Really close. 45. Remember, it's a quarter of what I have left. So a quarter of 60 would be 15. So I would take 15 away from 60, and that would leave me with 45. Now, before we go any further, I want to point out that what we care about is the part that's left. So we can find that with this two-step process. Find a quarter of what I have and subtract it off. But what we want is to know what's the 3/4 that's left. So I could do this in one step if I actually found 3/4 of 80. So instead of finding 1/4 and taking it away, I could say, well, what I care about is the 3/4 that's left. So what's 3/4 of 80? 60. You guys are finding that the same, you guys are finding, I should say, the same amount, just with sort of a two-step process. We can actually simplify that down to a one-step process. If I take 60 and multiply it by 3/4, instead of 1/4, but multiply it by 3/4, I would get that remaining amount. So if I take 45 and find 3/4 of 45, what do we get? Perfect, 33.75. And then one last time for me, what do we get left after that fourth person? Yeah, 25.3125. Good. Is the sequence that I have here arithmetic or geometric? Why is it geometric? Exactly. The sequence is geometric because we multiply by 3/4 each time to find the remaining area. We're multiplying by the same amount each time, so that makes this geometric. Now let's write our recursive and explicit formulas to represent this scenario. So remember, recursive is the one that's based on the previous term. So here, our new term would be 3/4 times the previous term. And then our explicit formula for geometric sequence, the explicit formula for a geometric sequence is the one that's got that exponent. So again, I'm going to use the first term in our sequence, which is 80 here. And then my explicit formula would be a sub n equals 80 times 3/4 to the n minus 1. Now let's talk for just a second about why we're using an exponent for this one. Why for these geometric sequences are we writing an explicit formula with an exponent? So I want you to think about a different sequence here. Let's say our starting term is 10. And to get the next term, I have to multiply by 2. That would tell me my second term is 20. And then to get the next term, I have to multiply by 2. And to get the next term, I have to multiply by 2. And to get the next term, I have to multiply by 2. Let's say we multiply by 2 each time. So if I want there's 1, 2, 3, 4. If I want the fifth term, I would have to multiply by 2 4 times. What's another way that I could write this, that I want to multiply by 2 all those times? How else could I represent that? With an exponent, right? This is the same as 2 to the 4th. That tells me how many times to multiply by 2. That's the same idea here. We're starting with 80, and then we're going to multiply by 3/4, however many times we need to get the term that we want. So this is just a shorthand way to say keep multiplying by 3/4. Multiply by 3/4 this many times. Okay? That's why this one looks like an exponential function. Looks like an exponent. So now let's find a couple of those future terms. So if we find our sixth term here, that means we're going to plug 6 in for n. So this would be 80 times 3/4 to the 6 minus 1. Be careful as you type these in your calculator. I would throw that fraction in parentheses just like we did the other day. So we make sure we tell our calculator it's the whole fraction that gets the exponent, not just the 3. And then for these guys, you're going to get some bigger decimals. So go ahead and round to 2 decimal places for me. So it spit out a fraction for you. I would arrow up to select your answer and hit enter so you get it in the next line. And then if you arrow into the problem and put a decimal at the end, that will give you a decimal. I'll show you it on my calculator too. So if I type in 80 times 3/4 to the 6 minus 1, remember to get your exponent, it's this button that kind of looks like a mountain. And it gives me that fraction, so I'm going to arrow up to select it. And then if you go back in and just put a decimal, it will give you your answer as a decimal. You can also do, I think Control Enter gives you that approximation. I'll come take a look at your calculator in just a minute. But we should get, if I round to 2 decimal places, 18.98. And then try the 20th term. Try that one. If you know your answer is going to come out to be a decimal, and you just type a decimal somewhere in your problem. So if I were going to type this one in, I know it's going to be a decimal. So I could type 80 with just the point after it. It should just spit it out as a decimal automatically. So we would get 0.34 here Does it make sense that we would have a really small number for our 20th term? Why? Why would I expect a small number here? Yeah, I'm taking away bits of this paper every time. So at this point, 20 people have cut away a part of my paper. Should make sense that I only have a little bit left. Questions on number 17, or page 17, I should say. Okay, we've got one more we're going to look at for today. I'm going to help you with the setup on this, and then I want you guys to write the formulas. So for problem number 3 on the next page, page 18, this says that the table shows 2 animal populations growing over time. So population A and population B. Population A starts with a population of 23,000, and then 29,000, and then 35,000, and then 41,000, and then 47,000. What's happening here? It's going up by 6,000 each time. We're adding 6,000 each time. So what type of sequence is population A? Yeah, population A is arithmetic. What about population B? What's happening with population B? Can we add the same thing each time for population B? No. So if I look at the difference between my first 2 terms, that's not the same as the difference between my next 2 terms. So it's not arithmetic. I can rule that out because I don't have the same thing each time. The next thing I would want to check is, could this sequence be geometric? Is that an option? So for some of our previous sequences, if I go back here for just a second, we could look at those numbers and tell what we multiplied by each time. So 2, 8, 32, you probably could pick out that you're multiplying by 4 each time there. Or maybe even in here, 3, 6, 12, I could pick out I'm multiplying by 2 each time. But with the numbers I have here, I can't recognize what that multiple is. So if I think it might be a geometric sequence, but I'm not sure what I multiply by each time, I can figure that out. We talked about this earlier in our unit, but I want to review it here. So if I'm not sure what to multiply by, I can figure out what that ratio is. So I'm going to take the second term and divide by the first term. And I got 1.2. So that means if I take my first term, 3125, and multiply by 1.2, I should get the second term. And I did. Now, if this is a geometric sequence, that should be true for all of my terms. So if I take 3,750 and multiply by 1.2, I should get the next term in the sequence. And I do. It's a good idea to try these a couple of times. And each time I multiply, so there, 4,500 times 1.2, I get the next term in the sequence. That means that this is geometric, and our common ratio would be 1.2. Does that make sense? Okay. So what I want you guys to do now, that we know A is arithmetic and B is geometric, I want you to write a recursive and an explicit formula for each of those sequences. last quiz. I always collect back your graded work. So I want you to look at these and ask questions if you have any. But don't put them away because I will take them back from you. So 1.2, as a decimal, that even on your calculator can be 1.2. Exponent is it's not wrong to write it. Go ahead and check your formulas when you're finished. I used the first population number that they gave me for A and B. So my explicit formulas are based on that first term being 23,000 for population A and 3,125 for population B. So if you used a different number, then these portions will be different in your explicit formula. Questions for me on 2 or 3? Okay, we have one last problem that we're going to take a look at for today. Number 4 says graph your explicit functions. That would be this guy and this guy. And what it wants to know is, does population B ever overtake or exceed population A? So if I take a look at my table, population A starts significantly higher than population B. They're both growing, but at different rates. For population A, I add 6,000 each year. For population B, I multiply by 1.2 each year. So they're still pretty far apart after 4 years. What we want to know is at any point does population B catch up and exceed population A? So we're going to take a look at our graphs on our calculator for this one. So I'm going to go ahead and on my calculator, make a graph, and I'm going to graph each of my explicit formulas. So I'm going to type them in as they appear on my page, as I have written them, except instead of n, I'm going to use x when I type them in my calculator. So for my first explicit function, this is 6,000 times x minus 1 plus 23,000. And then for my second function, I'm going to hit the tab key here to bring up my entry line again. This is 3125 times 1.2. And then again, that mountain button for the exponent, that's a caret is what that's called. And then my exponent here would be x minus 1. There's my second function. So I can't even see that second graph on here. So what I'm going to do is adjust my zoom here. I'm going to hit the menu key and I'm going to go down to zoom. And when I can't even see a hint of the function, I like to use zoom fit. So here's the picture I get from zoom fit. So that blue line was our first formula, our population A. And the red, this sort of curve here, is our second explicit formula for population B. I'm going to zoom out just a little bit more. So menu, zoom, out. And let's zoom out just a little bit more. So when I zoom out just a little bit more, I can see that population B starts to really take off. And it does, in fact, overtake or pass population A. Right? I do end up with a part of my red function that's above my blue function. So does population B ever overtake population A? Yes. When? Well, for that, I need to go back on my calculator and figure out exactly where that point is. So I'm going to go to Menu, Analyze Graph, and then I want to find that intersection. So with my dashed line here, I'm going to click on either side of that intersection point, and it will give me those coordinates. So my point here is 22.25, 150,508. Now it's asking me when. The when would be that n value. The y would be how many animals we have at the time. So we're looking at sometime after 22 years. So yes, after 22 years. Yes. How did we get a decimal for an answer? Oh, menu. And then go down to analyze graph. And then we want that point of intersection, so go down to intersection. And that will give you that sort of dashed line. So a problem like question number 4 isn't something that I'm going to ask you on, let's say, your unit quiz, but it is kind of a preview for what we're going to look at as we move past Unit 6 in Algebra 1 and when we get into Algebra 2, being able to sort of compare values for different functions and being able to use our graphs to help us with that. Questions for me on page 18? Okay. So that's the end of our sort of notes for today. For the remaining class time and what you can think of as your homework for today, I want you to make sure that you've completed all of your work in your packet up to page 18. Okay, that means you've done all your homework. You've done those 2 Khan Academy assignments we had earlier in the unit. you are good to go up to page 18. Tomorrow, we're going to work on review. If you are hopelessly bored and cannot wait to start your review, it starts on page 19. Please do not try to get all of your review done in the next 7 minutes, okay? We're going to work on review and have questions tomorrow. So make sure that you have done all of your regular homework, you're caught up on notes through page 18, and then tomorrow we'll start to look at those review